In supervised learning or classification, we focus on an individual data instance at one time and try to make a prediction or decision based on features of that single instance. While we may have built a model based on a large number of training samples, testing is conducted more or less on an isolated data instance, where the result of other test data has no impact. In reality, however, we have many situations and problems that are much more complex than what can be treated as classification for a number of reasons. For one, there might not be a clearly defined set of labels or training data for supervised learning. Perhaps it is not possible to tell whether an action or decision is right or wrong, true or false under the current circumstance. Rather, it should be focused on what is better or worse, what is improving or degrading. So the objective here has more to do with optimization than classification. More important, it normally takes more than one trials to figure out what is working versus what is not. So whatever learning model we employ, we'll have to analyze a sequence of actions and returns to identify an effective model. Let's take playing a soccer game, for example. Imagine if you are a striker, the success of your actions, either to pass a ball, to dribble, or to score, depends on your interactions with the environment. For example, who has the ball and where the ball is going, where your teammates are or running to, and where players on the other side are or moving toward. It is a very dynamic environment that is constantly changing, and you need to be alert about what may happen next so you can be there in the right place at the right moment, such as to receive a ball or to score. The soccer game example illustrates several important concepts in reinforcement learning. The first is the agent, which is a software program in the context of creating a learning algorithm, but it is just like a soccer player who learns and adapts to perform actions, such as to play in the soccer game. The environment refers to the entire dynamically changing setting where the agent operates. Okay? The environment can be likened to the soccer field with the players and referees, their interactions and timing of everything. The state of the environment, such as the location of the ball and the moving speeds of players, for example, in the soccer game example. Reward or penalty as a result of an agent's action. So once the agent performs an action, it receives certain penalties or awards. For example, in the soccer game, there are big awards such as scoring or penalties such as receiving a red card. But there are also minor rewards such as passing the balls accurately and being able to have longer possession. Through actions and interactions with the environment, it is possible for an agent to gain knowledge and improve its action. So here is the concept of the policy, which is the method or strategy an agent uses to act on its knowledge to maximize its long-term rewards. Q-learning is a specific reinforcement learning policy in which the agent keeps track of rewards associated with each state and action. Specifically, the agent stores rewards in a so-called Q table like this. There are rows and columns. In Q table, the rows, the S1 to Sn, are the possible states, and the columns are all the actions. And the Q table is initiated with 0 values, and the values will get updated when an agent performs an action and receives an award at a particular state from the environment. Suppose at time t, the agent is at the state of st, performs an action at, and receives an reward of rt. Here is one strategy to update the Q table. So here, the beta is referred to as the learning rate. The greater the beta value, the more aggressive the updating strategy. And gamma is the discount factor for future awards. So the greater gamma is, the strategy tends to put more emphasis on long-term rewards. The Q learning updating strategy is to take the Q value. This Q STAT is the current value of action T at state ST. And so 1 minus the learning rate is basically the portion to retain the current value. And then the beta times RT is how much you want to use the reward or penalty to update the Q value here. And then gamma is to multiply or to discount the amount from future awards. Okay, so this is the kind of a general idea of Q learning. In Q learning, or in any reinforcement learning, an agent learns from trials and errors. So learning requires random exploration in the environment so that you can encounter different situations and learn from those situations. At some point, the agent may gain sufficient knowledge to make wiser decisions based on a trained Q table. However, in order to allow opportunities for continued learning, one should avoid complete exploitation of Q table for action selection. For the trade-off between exploration and exploitation, we should introduce a third parameter, epsilon. So at time t, with epsilon probability, the agent will select a random action. So this is for the agent to explore with the epsilon probability. And then with 1 minus epsilon probability, the agent selects an action based on the Q table. The second probability, 1 minus epsilon here, is to actually exploit, to use the Q table. To understand the whole process of Q learning and what it can do, let's look at a very specific example, the Taxicab example. So it's part of the OpenAI Gym environment, and the taxi task is a simplified version of driving a taxi cab in city blocks. Something like this. Here you see a 5x5 area of city blocks, more like a parking lot. And in this environment, the problem for the taxi is to be able to pick up a passenger from a location, such as G here, and drop off the passenger at another location, such as Y, and try to travel as little as possible. So you want to deliver the passenger without too much cost of driving it. In each state, such as the configuration here, where there is the pickup location at G and a drop-off location at Y, the taxi cab here has multiple options. In particular, there are 6 actions it can select from. The first is to move south, or to move north, to move east or west, or the taxi cab can also decide to pick up a passenger or drop off the passenger from the location. So in total, there are 6 actions the taxi cab can perform. Of course, some actions is not going to work, such as to move west here, because there's a wall here, so the taxi cannot move. Or to pick up from the street, which is not allowed. Now, there are related rewards and penalties associated with each action at each state. -1 is a penalty for each action and move. So this is to incur some penalty for the cost. Now, if you try to do something illegal, such as to pick up from the street or to drop off a passenger on the street, there's a -10 points penalty for that illegal pickup and drop off. The major reward in this particular environment is the 20 points for a successful delivery of the passenger. So here, if the cab can drive to the pickup location, picks up the passenger, and then drive all the way to the Y location to drop off the passenger, then the cab will receive 20 points. Of course, along the way, each action or each stop it goes, there's a -1 penalty. Okay, so hopefully in the end, if the cab is smart enough, it will try to take the shortest path and then make the delivery so it can actually make a profit. Here's another configuration where the pickup location is here, is at Y. So the cab has to drive to Y location and then move back to G to deliver the passenger. In order to understand Q learning first, let's look at action without learning. So what we are going to do here is just to start with the dummy version of the taxi cab. So what the cab will do in this version is that it will simply select a random action at each state and thus to learn from the penalty. Okay, so everything is random here. Let's take a look at what the cab is capable of doing. So here we know that the pickup location is Y and the destination is R. So the cab has to move to Y and then go to R. But in this particular situation with random actions, each time the cab just randomly selects an action, it looks like it has no clue of what should be done next. So we can tell that the cab is fooling around and its moves and actions are random and meaningless. By looking at the behavior of the cab, we can hardly have any confidence in it to develop any intelligence and to perform a better job over time. So the strategy of random actions simply does not work here. And as you can see in the final result, it takes 200 steps. And in the end, the total reward is minus. So there's lots of penalty because this agent, the cab here, does not really learn. Now let's see how the agent can explore and learn in the environment. Let's follow the Q learning idea. So the agent cab can learn from its failures and successes. In particular, we would like the agent to remember what works versus what does not. That is, what are the past rewards or penalties for each action taken in each state. We know there are 6 different actions the cab can select from. But how many states are there? Let's find out. So here are factors to be considered in the combination of states. So we know the cab can be at one of the 5 times 5 blocks. So there are 25 blocks and the cab can be in any of these locations. The passenger can be picked up from one of the 4 locations. So the passenger may be waiting in one of those locations, or if the passenger has been picked up, then he or she is in the cab. So there are actually 5 different locations the passenger may be. And then the cab is to drop off the passenger at one of the 4 locations. So there's another factor of 4 locations for the drop off. And so we put all the factors together. There are 500 different combinations or different states for the Q-learning. So we need to create a Q table of 500 rows states times 6 columns for the actions. Okay, so we can do that. And the result of that is that we start with the Q table with all 0 values. And here we only show the first 10 states. And so as you can see, there are 6 columns in there for each state from 0, 1, 2, 3, 4, 5 until 499, which is 500 states. Okay, so this is kind of the initial Q table, and hopefully with learning and training, we'll be able to update this Q table, and the agent or cab can use the knowledge in the Q table to perform better in the jobs. We'll let the agent explore a little bit with the probability epsilon equal to 0.1, which means the agent has 10% probability to explore and select random actions. This is for the exploration. And then 90% of probability to select the best action based on the Q table, based on its memory. After each action, the agent will receive a reward that will be used to update its Q table. Okay, and this is the algorithm that we looked at just now. Again, beta is the learning rate, and here we use 0.1 for the learning rate. Okay, so 0.1, we're going to use the penalty and future awards to update the current value, but 1 minus 0.1, which is 90%, we're going to retain the current value. And then gamma is 0.6, which is the discount here for the future reward, the best reward that you can obtain from future actions, which is 0.6. QSTAT is the current value for the state and the action. RT is the reward received from this particular action at that state. And then Q prime is the updated value in the Q table. So after training the agent or the cab for 100,000 times, which takes about a minute on the Mac, we obtain the following Q table. Okay, so this is the updated Q table after 100,000 trials. And then let's look at whether the agent can actually take advantage of the Q table with the updated values and perform a better job. So let's test the train model with the updated Q table, and we are going to test the agent for 100 tasks or 100 episodes to pick up and deliver the passenger. So let's take a look at the result here. So for example, the pickup here and the destination is at B. Okay. Another task, pickup at G to deliver drop off at B. Pickup at B to deliver to G. So it looks like each time the cab is capable of going directly to the pickup location and take the shortest path to the destination to drop off the passenger. And over time, we see that it actually accumulates reward. So this agent, after training, definitely performs better than the random model that we looked at earlier. So what happened? How did the agent actually learn? Let's look at a specific task here to make sense of the Q learning. So in this example here, in this particular state, the cab is right here at this particular location with the pickup a location of a passenger at B and the drop-off location at G. So the optimal move here is that the cab has to move south to reach B and select the pickup action and then turn around back to G to drop off the passenger there. So how does the cab learn to go south first? This is the very first step that leads to the success of the delivery. So how does it learn to go south first to maximize its long-term reward? Let's represent this decision making as a graph. So for example, at this particular state here, so in this particular state, let's call it 0 state, okay, with this configuration. And at this particular state, the cab has multiple options. We know 6 actions it can select from, right? Either to go north, to go east, to pick up, to drop off, to go west, or to go south. And so south is only one of the actions that you can perform. Okay, so you can think of the actions as the branches. When you take an action, so originally you state 0, you take an action of south. Now, after the action, the state will be changed. And so perhaps this becomes state 1. Okay, so the state will be changed. And then from here, you can select one of the 6 options or 6 actions again. So this whole process can be visualized as new branches from each one of the actions taken. So again, this is one state. You take an action, reach another state such as 1, and perhaps from 1 you take another option which reaches another. So we can continue on and on. But this is the graph representation of the actions. Now in particular here, how does the agent maximize its long-term reward? By moving south first. So very important, we want to understand the first step here. How does it get rewarded for the long term? Let's first look at the whole path. Okay, if we use the graph representation from state 0 and then you take south, so you take the action of south and it becomes state 1. And next you take the action of south again and that becomes state 2. Okay, so and then after that it performs a pickup and then it becomes state 3, because now even though the car is still in the same location, the passenger now is inside the cab, so it's a different state now. Okay, and so we'll continue all the way to east to turn around to north, right, and all the way to 8 to move north all the way to the destination. When you reach the destination, you are in state 8. And here, if the cab performs a drop-off, the state becomes 9 and it receives 20 points as the final reward. Okay? So the reward will only be given after the job is successfully done. But let's go all the way back to the first step here from 0 state, taking south, and see what it happens. So for the sake of discussion, let's suppose this is the very beginning of the learning and all values in the Q table are all 0. So by taking an action south, okay, by taking an action south action as state 0, we know there is a cost associated with each action. So the penalty will be -1. There's a cost like gasoline consumption. Okay, that is a penalty. So the agent will receive this -1 penalty, and that value will be used to update the Q value for state 0 with action south. So the Q 0 south will be updated using this formula here. So as we know, beta is the learning rate, which we use 0.1 here. So -1 minus beta is 0.9, which is the proportion of the current value we try to retain in the updating strategy. And because the initial Q value is 0, so this times 0 will become 0. Okay, but for the learning part, the 0.1 learning rate times the reward RT is -1 plus 0.6, which is gamma, the discount for future rewards. Now, at the very beginning, we know all values are 0, so even for the future rewards that you can imagine in the next step, there's nothing. So all rewards is 0 at this point. Okay, so 0.6 times 0 is 0, -1 times 0.1 is -0.1. So actually, by taking this action of going south, the agent actually will be penalized, and the Q value will actually be subtracted. So the Q value here for the 0 south for this particular action at state 0 will actually become negative. Right now, we can say that this value will become -0.1. So will the values of the other actions for the following states as well. You may start to wonder, how can the agent learn from this penalty? Because every action it takes receives a penalty, and the Q values on the path now become all negative. Now let's go to the final destination, where the agent reaches the drop-off location, and see what happens here, so that we can look back to the earlier actions to see what kind of benefit they may receive. Once the cab reaches the destination and selects the drop-off action at state 8. So basically from state 7 to state 8, you take the north action to reach state 8. Okay. At this particular state, the cab has reached the final drop-off location. And so at this state 8, if the agent performs the drop-off action, it's going to receive a reward of 20 points. And it's going to use this 20 points reward to update its Q table. So let's see how this Q value at state 8 and action drop-off will be updated with that reward. Okay, again, 1 minus beta, 0.9. And beta is 0.1 for the learning rate. And of course, initially, all values at 0, so this part will still be 0. But then we have the RT equal to 20. We have received 20 points for the drop-off. And for future, again, it's going to be 0. Okay, so, but what we get here is 0.1 times 20, which is 2. Okay, so the Q value for state 8 and action drop-off will become 2. So with the new updated value of 2 for drop-off at state 8, the agent will definitely favor this specific location and the action of drop-off at this particular state, right? So this particular action at that state will be favored. There's no doubt about it. But how about the previous actions at previous states leading to the drop-off? Because it's very important. If the agent did not take the first action to move south first, you can never achieve this final step. How do they get rewarded as well? Let's move a step back. Remember, in the Q table updating policy, we have this part for the current value to retain the current value. And then in the second part, for the learning we also have two parts. One is the reward for this particular action. The other is gamma times the maximum reward that you can receive from the next step. For example, next time when you continue to train the agent, and so at state 7, which is right here, okay, and so this is 7 state, and if you perform an action for north, which leads to state 8 right here, okay, and so 7 north, so state 7 north will be updated in addition to whatever reward this particular action at this particular state may receive, plus the current value. Now let's focus on this future award, okay? Because state 8 and the ability to drop off at state 8 is part of this t plus 1. Because if t here is 7, t plus 1, state 8, as part of the equation here. T plus 1 after performing north is actually a reference to the state 8. Okay, and so of course at state 8, the agent can decide to move north, to move south, to east, west to pick up, but there's also an option to drop off. And according to the Q table, remember just now, Q for state 8 and with the drop off action is 2. So this Q8 for drop off is definitely going to be the maximum value. Okay, so this will become 0.6 times 2 for future reward. So to update this value, what we take is going to be 0.6 times, of course, the learning rate is going to be 0.06 times 2, which will be used to update this particular action here. So the main takeaway here is that a reward at one state will be back propagated to an earlier state. With a sufficient number of iterations to train the agent, the rewards or penalties will be carried all the way back. So from 8 to 7, from 7 to 6, from 6 to 5, and all the way back to the 0 state. Okay. In the end, Q0 south will also be rewarded because in the end you have a successful drop off with 20 points reward, and with enough training this reward will become significant enough to influence the agent. So in the end, the reward received for drop off at state 8 will also have an impact on going south at state 0, even though they are only remotely connected. Overall, the Q learning policy will help improve the taxi cab's behavior toward greater long-term rewards. So let's compare the dummy cab and the train model side by side for a final comparison. So let's run the model. On the left is the random model, on the right is the train model. And it is easy to tell that while the random model continues to lose and accumulate penalties, the train model on the right is much smarter in knowing how to move directly to pick up and drop off location to maximize its long-term rewards. Applications of Q-learning certainly go beyond the simplified taxicab example here. A recent development is the AlphaGo that defeated the best human player in the Go game. One can also imagine a similar reinforcement learning policy to be used by a smart vacuum robot to maximize the amount of dirt it can pick up to make your rooms clean.